So today we are going to start using trigonometry in relations with triangles to do something called solving right triangles. What I mean by solving a right triangle is to find any missing pieces that we may have. Now we're going to expand on this a little further when we learn about what's called inverse trig, but we can start now. First, a couple of rules. All right, so here I have a right triangle, and I have the two angles. Here we're going to call this angle alpha, and here we're going to call that angle beta. I am going to label my sides. I don't know. Okay, so here we have y over here, x down there, and h for the hypotenuse. So, because right now we are dealing with right triangles, we can deduct a few things about our angles here, right? So again, we know a triangle has a total of 180 degrees. And because we're talking about right triangles, we already have 90 degrees accounted for, right? Our right angle is always going to be there. So we have left over 90 degrees between these two angles. We have a special name for that. We call alpha and beta complementary angles. All right, so no matter what shape this triangle is in, if you add the two angles other than the right angle, it will always get you 90 degrees. So with that, let's take a look at some of the trig involved. So if I'm looking at alpha and I take the sine of alpha, all right, so remember sine is opposite over hypotenuse. So my opposite would be x. My hypotenuse would be h. All right, obviously if they were numbers, we would make the fraction out of it, but we're just using the variables. The cosine of alpha would be the adjacent y, again, over our hypotenuse h. Now, if I change my viewpoint and now I'm looking at my beta angle, the sine of beta is the opposite y over the hypotenuse h. If I take the cosine of beta, that is going to get me the adjacent x over the hypotenuse h. So here we have a rule, or I guess you could say rule, with our angles in a triangle. I think I'm spelling complementary wrong, but whatever. Okay, we can say that the sine and the cosine of complementary angles are equal. Right? So without even, calculating anything, if I do the sine of 35 degrees, well, a complementary angle to 35 degrees would be, wow, I can't do math. 55. So the sine of 35 degrees is going to be equal to the cosine of 55 degrees, right? And that's because 55 plus 35 gets us that complementary, right? So if you plugged it in, again, we're talking about, remember, anytime we're dealing with sine and cosine, make sure you're in the proper form in your calculator. Right, so here I'm talking about degrees, so I want to make sure I'm in degree mode. So if I do the sine of 35, I get 0.57 whatever. If I do the cosine of 55, I get the same exact thing. And you may have noticed this when we were talking about when I showed you the special angles yesterday and their values. Okay, when I gave you that list, that little box of the sine, cosine, and tangent. Right, if we're dealing with a 30 degree and 60 degrees, right, a 30, 60, 90 triangle, 30 and 60 are complementary. So the sine of 30 degrees will be equal to the cosine of 60 degrees. They'll both be 1/2. All right, so we can use that to our advantage when we move on with some of our problems. Okay, and it may come up just as a general question, right? They may ask you, what is the sine of 35, or what is it equivalent to, right? So right away, you know, you can do this cosine of 55. All right, so trigonometry in real life, we use it for a lot of things. A lot of times we use it for directions. Okay, if we're talking about like when ships and planes travel, okay, we talk about how many degrees, what you turn, right? Northwest, south, east. We'll get to that stuff. That's called bearings. Another thing we do is we use it for like landscaping. Okay, constructing monuments, constructing statues, right? Anywhere that you can put a triangle, you can use trigonometry. So with that, we have two terms that you're going to see pop up. And that is angle of elevation and angle of depression. So when we talk about this, angle of elevation is when we go from a horizontal line and we're kind of looking up. Okay, so it's always in reference to some horizontal line. So you have a horizontal line and you're looking up, or you know, maybe you have a wire that's connecting to the top of your telephone pole, right? So if you're going up in that direction, we call that the angle of elevation. Now the angle of depression, we got to be careful. Again, we're doing it from a horizontal line, but now we're looking down. All right. So they use that a lot for flight, right? You know, if you're flying and you're looking down at the ground, right, you're looking 20 degrees at a angle of depression. So that means, you know, 20 degrees from where you're traveling in a horizontal direction. Right. So you might see these words pop up, especially when we're dealing with our word problems. So it is good to know those. All right. Let's see. Is there anything else that I want to talk about before we go into examples? Nah. Okay. Give me a second. I'm going to write down a problem, and then we'll go over it together. All right, so you're in Washington, D.C. You go over to the Washington Monument, and you're standing at the bottom of it, and you measure that distance from the base of the monument to you to be 115 feet. Have you guys ever heard of a sextant? It is it's a tool to use that a lot of times sailors use. It kind of looks, it's got like a little telescope thing, and it's got this, like, it's shaped like a V. And they use it to measure the angle to the sun, and then they use that in calculations on where they're heading, what time of day it is. They use it for a lot of things. Sometimes if you've seen the land surveyors, like right before they're starting to do construction somewhere, you'll see a guy with a big tripod, and it looks like a big camera, and he's taking measurements. Okay, so those are some tools that you can use to kind of measure angles in real life, right? So you click, you take a picture of something, that's your starting point, you move it over, you take another picture, and it tells you how many degrees you've turned, right? Or how many degrees up you're looking or down you're looking. So you have one of those on you, and you measure the angle of elevation to the top of the monument to be 78.3 degrees. So with this information, we can calculate how tall the monument is. All right. So anytime we're given a word problem like this, especially with triangles, I would highly recommend to draw it out. Obviously, it doesn't have to be perfect. This isn't, art class. All right. So there's our Washington Monument. Right, a very rough sketch. We're looking for its height. All right, I'm going to put the height in the middle, though, there. So we know from the base of the monument, right here, we're standing all the way over here. And this is 115 feet. So you take your tool, you measure it to the top, right? And then this angle here is going to be 78.3 degrees. So we want to find what's over there on our vertical point. So we're going to do two things. The first thing we're going to do is we have to determine which trigonometric function we need to use. We're going to usually stick with our three basic ones: sine, cosine, and tangent. So with my angle here, we label the side that we know, and we label the side that we're looking to solve. So here's my angle. So this 115 feet with reference to this is going to be my adjacent side. The height of the monument in my triangle, with this as my angle, this is going to be my opposite side. I'm going to call this y because it's vertical. So now you have to say to yourself, what function am I going to use that has a relationship of the opposite and the adjacent side? All right, so you can go back to the list that we came up with yesterday or last week. All right, so you're looking at these, and you're looking for opposite and adjacent, right? Or if you remember SOHCAHTOA, you can use that as well. All right, so opposite and adjacent, we're going to be dealing with the tangent. So right now, I'm just going to write out the rule for tangent, right? So the tangent of my angle is going to be the opposite side over the adjacent side. Now that we have our situation set up, we're going to substitute. So I'm going to take the tangent of 78.3 degrees, and that is going to equal the opposite, which we don't know, so I'm going to call that y, over the adjacent, 115. Now, depending on what you're using as a calculator, I wouldn't, well, either way, I wouldn't solve this yet. Right? I wouldn't find that until the end. I'm going to use my inverse operations first to get the y alone, to get our variable isolated. Right? So what's going on in between the y and this 115? Well, we're dividing them. Right? So if I want to get rid of that, I have to multiply both sides by 115. So the height is going to be 115 times the tangent of 78.3. Now, if you have a calculator like this, you can just type that in as you see it. So we just calculated that the height of the monument is about 555 feet, right? We'll say 555.3. Right? Now, if you don't have a calculator like this where you can type it all in, I would recommend calculating the trig part first, right? And then do not round if you can, right? So let's see. Let me bring out. So again, this is going to be slightly different if you have an iPhone, but similar, similar process. Right, so if you hold your phone in landscape mode, you get all of the fancy parts over here, or I think it's on your left side. Right, so with your phone, again, I'm in degree mode. We're good there. I can't hit tangent. Oh, okay, here I can. Tangent of 78.3. Last time I had an iPhone, you can't type it in like this. What you would have to do if you have an iPhone is you have to type in 78.3 and then hit the tangent button. All right, and then you would get some crazy decimal. From there, do not round this. You're just going to hit times and then 115. I didn't type 115. All right, no, that's plus times 115. There we go. Okay. Again, do not round. If I did the tangent of 78.3 and I said maybe 4.8, so I do 115 times 4.8. Nope, not that. All right, we're off by 3 feet. All right, now, obviously for this instance, we're just trying to estimate the height of the monument, right? It doesn't have to be accurate. But if you're doing measurements, for some science experiment, or if you're an engineer and you're doing measurements for maybe a bridge, there's a big difference between 555.3 feet and 552 feet, right? If you rounded like that, you'd end up with less material. You might not have enough to build whatever you're trying to build, blah, blah, blah. Okay, so we want to be as accurate as possible. Any questions about that? All right, let's do one more example. And this one, actually, you can use in real life. Now, I'm not expecting you guys to do this, but if you're so inclined to. Nope, I already messed up. My mistake. All right. So this is actually pretty interesting because I'm going to tie it into something cool in a second. So we got a tree, and it's casting a shadow, right? You measure the shadow to be 12 meters long. If you know the position of the sun, you know, in terms of degrees, how high it is in the sky, you can find the height of anything from its shadow. Okay, so here we have a similar situation to what we had up there, right? We have the base, we're looking for the height, and there is our angle of elevation. Right, so our setup, okay, again, I have I'm looking for the opposite, I have the adjacent, so I'm going to be dealing with tangent. So the tangent of 62 degrees is going to be the height of the tree over 12. Right? Or we can say that the height of the tree is going to be 12 times the tangent of 62 degrees. Right? So we can plug that in. Tangent 62. Right? So without actually measuring the tree or whatever we're looking at, okay, just using the shadow, we can find that the tree is 22.6 meters tall. Now, the reason, well, one of the, way back when, before, you know, all of these math rules were here and before we had precalculus and calculus, I forget who it was, I forget his name, but somebody in Egypt used this method to calculate the diameter of the Earth. Okay, so they used the shadows and they measured the shadows and they measured the sun, right? And they did their math and they were accurate within like something crazy, like 0.1%, right? So before we had any technology back in Egypt, like as they were building the pyramids, somebody calculated how far it was around the equator of the Earth just by looking at shadows. Okay. They also used this to prove that the Earth was round. What they did for that was they had two monuments, okay, and they measured where the sun was from the first monument and the second monument, and they looked at the shadow it casted. Right. So using those calculations, because the sun here would cast a small shadow compared to the sun here, which would cast a larger shadow. So they had two, you know, scientists or whatever they were at the time, go to two different places, build the same height monument, and they had them record all their, you know, the shadows and the times of the day, right? And using basic trigonometry, before it was really trigonometry, you know, we found, I don't want to say galactic measurements, but we found very, very large measurements just using some basic math. All right, any questions about solving triangles so far?
How long did it take them to find the diameter?
I don't think it was too long. Let me see if I can. I know if you watch, there's an old show. They actually remade it on Fox called Cosmos. And the original creator, his name is Carl Sagan. He does a really good piece on this. Let me see.
Thank you. I'll check it out.
His name was Oh, I don't know how to pronounce that. Eratosthenes? I don't know. yeah, I'll do some more research on that. But that's just a neat little side bit. I like to tie, science into all this stuff we do. All right. So